Suppose we have a smooth curve on a surface where the position vector to every point on the curve is defined by the parameter t. So the x coordinate is a function of t, and so is the y coordinate, and also the z coordinate. And this smooth curve is on a level surface of a differentiable function f. So the function is of 3 variables, and the level curve of the function is defined by f of x, y, and z is equal to a constant. So if we differentiate both sides with respect to the parameter t, we take the partial of f with respect to x and multiply by the derivative of x with respect to t, plus the partial with respect to y by dy dt, plus the partial of f with respect to z by dz dt. And differentiating a constant on the right hand side, we get 0. So we get a similar expression to a level curve of a function of 2 variables. So this expression is the dot product between a gradient of f and the velocity vector, being the vector that's tangent to the curve. And this is equal to 0. So this tells us that the gradient of f is orthogonal to the velocity vector of the curve at every point along the curve. So at a particular point P, all of the curves passing through this point on the level surface are orthogonal to the gradient vector at this point. So essentially all the tangent lines to these curves passing through P, so we have the slope of the tangent looking something like this, and for this curve it looks like this, and for the other curve we have a tangent line that looks like this. So these tangent lines for all these curves all lie in the same plane that goes through point P, and this plane is normal to the gradient vector, which is drawn here. So recall that a plane is defined by the dot product between a normal to the plane and a vector created by 2 points on the plane, and that's equal to 0. So if we take some point on this plane, being point Q, with coordinates x, y, and z, then we can write the equation of this tangent plane. So noting that point P has coordinates xp, yp, and zp, the equation of this tangent plane is the partial derivative of f with respect to x, being the first component of the gradient vector. So the gradient vector is the normal to the plane, and we multiply this by the x coordinate of some point on the plane minus the x coordinate of point P on the plane, which is the known point on the plane, and plus the partial of f with respect to y by y minus yp, plus the partial with respect to z by z minus zp, and that's equal to 0. So noting these partial derivatives are evaluated at point P. And furthermore, the normal line of the surface at point P is the line that passes through point P that's parallel to the gradient vector at this point. So recall that a line can be parametrized by the parameter t, and the line can be defined using the base point and the direction vector. So the x coordinate of the point on a normal line is the x coordinate of our base point, being the point on the line, plus the parameter t by the x component of the gradient vector, which is a partial of f with respect to x. noting that the gradient is evaluated at point P. And we have a similar equation for the y-coordinate. So we have yp plus the parameter t by the partial of f with respect to y, evaluated at P. And z is zp plus t by the partial of f with respect to z, evaluated at P. So note that this is the normal line to the level surface at point P. So the equations we derived only apply to a level surface at this stage. Suppose we want to find the plane tangent to a smooth surface. So we have a surface defined by a function of two variables, where f is a differentiable function, and we're finding the tangent plane to the surface at a point P. So if we take two curves passing through point P, so for example this curve has a tangent line that looks something like this, where this curve's in the plane parallel to the xz plane, and we have this other curve parallel to the yz plane, which has a tangent line that looks something like this. So if we take the coordinates of this point as xp, yp, and zp, then a point on this tangent line, which we'll call q, has a variable x coordinate, a fixed y coordinate, and a variable z coordinate. So noting that this curve is parallel to the xz plane. So therefore the equation of this tangent line is z minus zp is equal to the slope of the tangent to the curve at P, which is the partial derivative of f with respect to x evaluated at P, by x minus xp. So this is the general equation of a line. So that's our first tangent line. And if we choose a point R on the other tangent line, where the curve lies in the plane parallel to the yz plane, so in this case the x coordinate is xp being fixed, and the y and z coordinates are variable. So our second tangent line has an equation z minus zp is equal to the partial of f with respect to y evaluated at P. So noting the plane of this curve is parallel to the yz plane, so the tangent line is also parallel to the yz plane. And that's multiplied by y minus yp. So that's our second tangent line. So if we arbitrarily choose an x coordinate of xp plus 1 on this tangent line, then we can calculate the z coordinate. So therefore this equation would give z minus zp is equal to the partial of f with respect to x evaluated at P, multiplied by xp plus 1 minus xp, which is 1. So therefore the tangent vector along this line has an x component of 1, a y component of 0, and a z component of the partial of f with respect to x, evaluated at P. And in a similar way, we can get a vector parallel to this tangent line. So we can take y as yp plus 1. So that gives z minus zp is equal to the partial of f with respect to y, evaluated at P, by yp plus 1 minus yp, which is 1. So the tangent vector has components of 0 in the x direction, 1 in the y direction, and the partial of f with respect to y, evaluated at P in the z direction. And therefore to find the normal to the tangent plane, we take the cross product between these two vectors. So writing the determinant form of the cross product, we have the unit vectors in the first row, and in the second row we have 1, 0, and the partial of f with respect to x, evaluated at p, and 0, 1, and the partial of f with respect to y, evaluated at p. So the I component gives 0 minus the partial of f with respect to x at p, and the j component is minus the partial of f with respect to y at p, and the k component is 1. And now we can obtain the equation of the tangent plane to the surface at point P. So taking the dot product between this normal vector and a vector formed by 2 points on the plane, with one of those points being point P. So we have the first component of the normal vector, which is minus a partial of f with respect to x at P, by the x coordinate of this general point minus the x coordinate of point P, and minus the second component of the normal vector by y minus yp, and plus the third component, which is 1, by z minus zp, and that's equal to 0. And if we divide through by -1, our final equation looks like this, being the equation of the plane that's tangent to the surface at point P. We can estimate how much a function changes as we move a small distance from a base point to another nearby point. So we move a distance of ds. Now for functions of one variable, we move from one x value, which we'll call xp, by a small distance dx. So using the slope of the tangent to the curve at P, we approximated the change in the function, being dy, as the derivative evaluated at xp multiplied by dx. Now for a function of two variables, we estimate the change in a differentiable function f when we move a small distance ds from point P in the direction of u using the directional derivative. So we have the change in f is the derivative of f in the direction of u by the increment ds being the small distance that we moved from point P. Noting the directional derivative is evaluated at P. So the directional derivative is the dot product between the gradient of f and the direction vector u, where the gradient is evaluated at point P, and that's multiplied by the small change ds. Recall that for a function of one variable, we approximated the value of the function at some point x using the value of the function at a base point xp. So this is the value of the function at xp plus the derivative evaluated at xp, giving the slope of the tangent at xp multiplied by delta x. So delta x was x minus xp. So that gives this value of f of x being the linear approximation. Now we can extend this approximation to a function of two variables. So for example, if we move from point P, which has coordinates xp and yp, to a nearby point in the plane, which has coordinates x and y, then similar to a linear approximation to a function of one variable, we can approximate f at x and y using the value of f at point P, which has coordinates xp and yp, plus the partial derivative with respect to x evaluated at point P by delta x. So noting delta x in this case is x minus xp, plus the change in f in the y direction. So we have the partial derivative of f with respect to y evaluated at xp, yp, being the coordinates of point P, multiplied by delta y, where delta y is y minus yp. So this is the value of the function at point P, and this is the approximated value of the function at point Q. So we write this approximation to the function as L of x and y, being the linearization of the function at a point P with these coordinates, and we call the approximation to the function of x and y by L of x and y as the standard linear approximation of the function at point P. So as you can imagine, the larger delta x is, and also delta y, the worse the approximation gets. And this can be seen if you recall the equation of the tangent plane to the surface at point P. So we had the partial of the function with respect to x evaluated at point P by x minus xp, plus the partial of f with respect to y evaluated at point P by y minus yp minus z minus zp is equal to 0. So taking z to the other side of the equation, we can write this as z is equal to zp plus these terms. So therefore we can say that this is a linear approximation to z, where the point Q has coordinates x, y, and the z coordinate is L of x and y. So the point will be on a tangent plane, which we can see moves away from the surface. The linearization of a function f, giving a linear approximation, results in some error. So the error in the standard linear approximation of the function f of two variables is the difference between the value of the function and a linear approximation. And to get the magnitude of the error, we'll just take the absolute value. So if our function has continuous first order partial derivatives and also second order partial derivatives, being the partial with respect to x, y, and the mixed derivative of x and y, so these must be continuous throughout an open set in the domain of the function that contains a rectangle which is centered around point P, where point P has some x and y coordinate, and we take M as any upper bound for the values of the second order partial derivatives, so it's larger than the absolute values of these partial derivatives. Then the error that results by replacing the function f by its linearization, being the linearization of x and y, which we've seen has the following form. satisfies the following inequality. So the magnitude of the error of the standard linear approximation is less than or equal to 1/2 by the upper bound for the second order partial derivatives by the absolute value of x minus xp plus the absolute value of y minus yp all squared. So this error bound can be obtained from the Taylor polynomial approximation of the function near point P. So we have the function of x and y is approximately equal to the function evaluated at P plus the first order terms. So we have the partial of f with respect to x at P by x minus xp plus the partial of f with respect to y evaluated at P by y minus yp plus the second order terms, which is a second order partial derivative with respect to x on 2 factorial by x minus xp squared, noting that all the derivatives are evaluated at point P, plus the mixed derivative with respect to x and y evaluated at P by x minus xp by y minus yp plus a second order partial derivative with respect to y evaluated at P on 2 factorial by y minus yp squared. So the error bound consists of the next higher order terms in the Taylor series, similar to what we found when we determined the error bound for the Taylor polynomial approximations of functions of one variable. And if we factor out 1/2, so this becomes a 2, and we get rid of these 2's in the denominator and replace the partial derivatives with the upper bound being m, then we can factor out m and get rid of these partial derivatives. So we'll just move these across, and this here is our error bound, which we can also simplify. So we have 1/2 by m by x minus xp plus y minus yp all squared. So to ensure we get positive values to get the maximum upper bound, then we replace these with absolute values. And therefore the absolute value of the error in our linear approximation to the function f is less than or equal to the error bound. So to make the error as small as possible, then we want to make delta x and delta y as small as possible, which gives a better approximation to the function. Recall for a single variable function, if we move from a point with a value of xp to xp plus a small increment dx, then the small change in f is approximated by the derivative evaluated at xp by the small change in x. So the larger the derivative, the larger the change in f due to a small change in x. Now in contrast, we can obtain a differential for a function of 2 variables by moving from a point with coordinates xp and yp in the xy plane to a nearby point with coordinates xp plus dx and yp plus dy, which gives the resulting change as the partial derivative of f with respect to x evaluated at p by dx plus the partial with respect to y evaluated at point P by dy. So recall the analogy to the linearization of f, where we had delta f was the linearization minus the function evaluated at point P, and on the other side of the equation we had delta x and delta y. And this is called the total differential of f. We can extend the linearization of a function, the error bound, and the total differential to functions of three variables. So the linearization of the function of three variables, denoted L of x, y, and z, at a point P is the function evaluated at point P plus the partial derivative with respect to x evaluated at P by delta x plus the partial with respect to y evaluated at P by delta y plus the partial with respect to z evaluated at P by delta z. So here delta x is x minus xp, and similarly delta y is y minus yp, and delta z is z minus zp. And now for the error bound, if we have a region being a closed rectangular solid that's centered at point P, and this rectangle lies inside an open region where the second partial derivatives of f are all continuous. So for a function of three variables, we have the second order partials with respect to x, y, and z, and also the mixed derivatives with respect to x and y, x and z, and y and z. So these partial derivatives are continuous in the open region that this rectangular solid lies in. And if we suppose the absolute values of these second order derivatives are all bounded, so they're smaller than or equal to some value m, throughout this rectangular solid, then the error in our approximation, which will be a function of three variables, being equal to the linearization of the function minus the exact value at x, y, and z, and we take the absolute value, is bounded throughout this rectangle by a similar inequality to the two variable case. So we have 1/2 m by the absolute value of x minus xp plus the absolute value of y minus yp plus the absolute value of z minus zp squared. So note that delta x, y, and z is restricted to this rectangular solid. And furthermore, if the second partial derivatives of f are continuous, then the total differential, due to a small change from point P to a point that's near P, so we have x plus an increment dx, and y plus a y increment, and zp plus a z increment, is written as follows, where the partial derivatives are evaluated at point P. So we have the partial with respect to x by dx plus the partial with respect to y evaluated at P by dy plus the partial with respect to z evaluated at P by dz. Find equations with a tangent plane, a normal line, at the given point on this surface. So this here is a level surface of a function of 3 variables because the function is equal to a constant. So the equation of the tangent plane in this case is the partial derivative with respect to x by x minus the x coordinate of the point on the plane, which is 1, plus the partial with respect to y by y minus the y coordinate of that point, plus the partial with respect to z by z minus the z coordinate of p, and that's equal to 0. And note these partial derivatives are evaluated at the point. So the partial with respect to x is 2x, and with respect to y is 2y, and similarly with respect to z is 2z. And evaluating these at point P, we have 2x is equal to 2, 2y is 6, and 2z is 4. So that gives the equation of the tangent plane. So we'll just replace these partial derivatives with the evaluated values, being 2, 6, and 4. And if we simplify this a bit further, we have 2x plus 6y plus 4z, and minus 2 minus 18 is minus 20, minus 8 is negative 28, and that's equal to 0. And you can further divide through by 2, so we get x plus 3y plus 2z, and adding 28 on 2 to both sides, we get 14. And the normal line at the given point has an equation in the x direction being equal to the x coordinate of the base point, which is 1, plus the x component of the direction vector, which is a partial of f with respect to x, multiplied by the parameter t. So this equation locates the x coordinate of a point on the line using the parameter t. And similarly y is yp plus the partial of f with respect to y by the parameter t, and the z coordinate of the point on the line is 2 plus 4 multiplied by t. Find an equation for the tangent plane to the surface described by the following function at the given point. So in this case, this is not a level surface, so we can apply the following equation to obtain a tangent plane. So we have the partial of f with respect to x evaluated at point P by x minus the x coordinate of point P plus the partial with respect to y at point P by y minus the y coordinate of P, and minus z minus the z coordinate of point P, and that's equal to 0. So note that we can write z as 2y minus x to the 1/2. So therefore the partial of f with respect to x is minus 1/2 by 2y minus x to the negative 1/2. And the partial with respect to y is 2 by 1/2, which is 1, by 2y minus x to the negative 1/2. So we're just applying the chain rule. And evaluating this at point P, we have 2 by y, which is 2, minus x, which is 1, gives 1 to the negative 1/2. So this partial evaluates to minus 1/2. And similarly, this expression evaluates to 1 to the negative 1/2, which is 1. And now we can replace these partial derivatives with the evaluated values. So we get minus a half and 1. So we can multiply through by 2 to get rid of the fraction. And we can write the equation of the tangent plane as minus x plus 2y minus 2z, and minus 1 by minus 1 is 1, minus 2 is negative 1, plus 2 is 1. So we get plus 1 is 0. Find the parametric equations for the line that is tangent to the curve formed by the intersection of these surfaces at the given point. So we see that these are level surfaces because the function in both cases is equal to a constant. So the gradients of both surfaces at the given point will be perpendicular to each surface at that point. So if we find the gradient of the first surface, so we'll define this by function f, that's equal to the partial with respect to x in the I direction, plus the partial with respect to y in the j direction, and plus the partial with respect to z in the k direction. So if we evaluate this at point P, we get 2i plus 2j plus k. And the gradient of the second surface, which we'll define by function g, is equal to 1 in the k direction, given by the partial with respect to z. So evaluated at point P, we get the same result. So given the gradient of f is perpendicular to this surface, and the gradient of g is perpendicular to this surface, which is a plane, then we can take the cross product between the two to get the vector that is tangent to the intersection curve. So we have the unit vectors in the first row, and the components of the gradient of f in the second row being 2, 2 and 1, and the components of the gradient of g, which is 0, 0 and 1. So what we get is 2 in the I direction, minus 2 in the j direction, and plus 0 in the k direction. So the equation of the tangent line gives the x coordinate of a point on a line, which is equal to the x coordinate of the base point, plus the direction of the tangent vector by the parameter t, and the y coordinate of a point on a line is minus 1, minus 2t, and the z coordinate is equal to 2, plus the component of the tangent vector in the z direction, which is 0 by t. Estimate the change in the function if a point q moves from point P by a distance of 0.1 units in the direction of the given vector. So recall the change in f is the directional derivative in the direction of u, which is the dot product between a gradient of f evaluated at point P and the unit vector, multiplied by the incremental change in that direction. So note that this here is not a unit vector because it doesn't have a length of 1. So we need to normalize it. So taking the magnitude of the vector, we get the square root of 1 squared plus negative 2 squared plus 3 squared, which gives us square root of 14. So the unit vector has an I component of 1 on root 14 in the I direction, minus 2 on root 14 in the j direction, and plus 3 on root 14 in the k direction. And evaluating the partial of f with respect to x by the chain rule, we get 1/2 by 2x, which is x, by x squared plus y plus z squared to the minus 1/2. And similarly, the partial with respect to y is 1/2 by 1 by x squared plus y plus z squared to the minus 1/2. And the partial with respect to z is similar to that of x. So we get 2z by 1/2 by x squared plus y plus z squared to the minus 1/2. And if we evaluate these at point P, and evaluating the expression in the brackets, we substitute for x, so that gives 9, y is 0, and z squared is 16. So here we have x, which is 3, on the square root of 25, or 5. And the partial of f with respect to y is 1/2 on root 25, which is 1 on 10. And this partial derivative evaluates to 4 on root 25, or 4 on 5. And now we can evaluate this dot product. So we get df is equal to 3 on 5 by 1 on root 14 plus 1 on 10 by minus 2 on root 14 plus 4 on 5 by 3 on root 14. And that's multiplied by the increment of 0.1. So multiplying this out, the estimated change in the function is 0.075 units. Find the linearization of the given function at the given point and an upper bound in the error in the approximation over the given rectangle. So we have the linearization at point P is the function evaluated at P. So we have the function of 1 and pi on 4 plus the partial derivative with respect to x evaluated at P by x minus the x coordinate plus the partial with respect to y evaluated at P by y minus a y coordinate of point P. So evaluating the function at x equals 1 and y is pi on 4, we get e to the power of 1 by sine pi on 4, which is 1 on root 2. And the partial with respect to x is e to the x by sine y. And evaluated at point P, we also get e on root 2. And the partial with respect to y is e to the x cosine y. And evaluated at point P, we also get e on root 2. So now we can replace these terms, which gives the linearization of the function at point P. And to find the upper bound for the error, we have the absolute value of the error is less than or equal to 1/2 by a constant m by the absolute value of x minus 1 plus the absolute value of y minus 3. And that's squared. So if we evaluate the second partial derivatives, we get the second partial derivative with respect to x as e to the x sine y And the second partial derivative with respect to y is minus e to the x sine y. And the mixed partial derivative with respect to x and y. So we can just differentiate this with respect to y. So that gives e to the x cosine y. And evaluating these at point P, we again get e on root 2 minus e on root 2 and e on root 2. So m is the largest of the absolute values of these derivatives. So that would be e on root 2. And to obtain the upper bound over this rectangle, which restricts the region where we find the linear approximation, to obtain a desired accuracy. So if this is the point P, our x coordinate and y coordinate of the nearby point must be within this rectangle, having a half width of 0.2 for both dimensions. So we'll just replace these absolute values by 0.2. And calculating this out, we get the upper bound for the error being 0.15. A cone-shaped funnel, so it'll have a small hole in it, is designed to have a radius of 2 centimeters and a height of 10 centimeters. Determine how sensitive the volume of the funnel is to small changes in the radius and height. So the volume of a cone is 1/3 by pi r squared by h, and a differential change in the volume is the partial derivative of the volume with respect to the radius by the incremental change in the radius plus the partial of the volume with respect to the height of the cone by the incremental change in the height. And note that we're evaluating these for a given radius and height of the cone. So the partial of the volume with respect to the radius is 2/3 by pi r h, and the partial derivative of the volume with respect to the height of the cone is 1/3 by pi r squared. So evaluating this partial derivative at the given radius and height of the cone, we get 40 pi on 3. And similarly, evaluating this partial derivative at 2 and 10 gives 4 pi on 3. So therefore, an incremental change in the radius causes 10 times the change in the volume of the cone than an incremental change in the height. Which makes sense, given the radius is a smaller dimension.